Got it. Hello, all. Quick welcome and everything. We so appreciate you joining us. You're getting live from Tel Aviv with Eran and Brandon. Normally join you from the middle of the country in Denver, but we're going to give a few extra minutes to get started today. And basic process here for everyone is going to be good. We're hitting people rolling in, which is great. Please on this, use the Q&A button. So if you look at the middle of your Zoom meeting, there's a great button down there that says Q&A. Go ahead and ask a bunch of those as we go through this. I will pester, bombard, annoy Eran with fun questions and keep it moving along. So use that for questions. We're going through it. A little background today. So thank you all for joining us. My name is Brandon Jung. I lead up ecosystems and sales and marketing and fun stuff here with Tabnine. And today we are going to be going through generative AI code and beyond. This is context of where this market came from, where it's headed. As you all know, or likely know since you're joining us, it is a little crazy out there. So be sure to lock up your bikes and everything else, because it's going to be a lot of fun. But from that standpoint, I'm going to introduce Eran. Eran is one of our founders here at Tabnine. Also serves as a professor up at Tabnine University up in just north of us in northern Israel, and has been building and working on this ever since back in his days in school and IBM. So he's going to give us a little bit of context, but honestly, this thing is not nearly as much fun if we don't give great feedback from you all. So ask a lot of questions. I will guide them and interject them as we're going. And I guess from there, Eran, it is yours. I'll stay on mute until questions come in, but we appreciate you all spend some time with us, and we'll give you a little start here, and we'll be with you for about the next 45 minutes. Thanks all for joining us. And Eran, give a little background where you're headed, anything you want us to know before we jump in, and then the floor is yours.
Yeah, thanks, Brandon. Thanks, everyone, for joining. This is going to be slightly technical. I'm going to talk a little bit about generative AI in general and large language models in general. And then I'll also dive into more specifics on how to use LLMs, large language models. And maybe if we have time, we'll even talk a little bit about how to better understand them, understand the limitations, and what they can do. So I guess I'll just jump in. I don't see your Q&A, Brendan, so you'll have to mediate that to me.
That's fine. You focus on giving us good context. I am the host,
Sure.
so my job is to try and keep you focused and answer as many questions as possible as they're coming in. So we'll do those as they roll. Don't worry about it.
All right, cool. All right, so let's just jump into it. So in the coming decade, all software will be written with the assistance of AI. We developed using AI. So I think code is going to be either generated using AI, reviewed using AI, tests are going to be generated using AI, and the thing may be even deployed using AI. And just, as a quick note, all the images on this presentation, all the figures like this, were also generated using AI. And whenever I have an AI generated image, you'll typically see also the prompt that I use to generate it. So you can reproduce it back at home. So this guy is software development with AI, neural network happy. As you can see, is happy. All right, so all images are going to be generated using AI as well. So again, in the coming decade, all software will be developed with the assistance of AI, but it's not really just about the future. 0.1% of the world's code is written by Tabnine today. So this is not something that is coming somewhere. This is already here. The future is here. Generative AI is changing everything, and it's also changing software development. So maybe a little bit more technically, you can think of the AI layer that is going to be added to your organization as another layer of the software development stack. So just like you have the source control, and just like you have the CI/CD pipeline, there's going to be an AI layer on top of both of these that is going to power and accelerate all stages of the software development lifecycle. And the way that it's going to do that, it's going to basically learn from all the data that is available here, all the kind of static data that you have stored in your source control, the passive data that you have in the source control and the CI/CD. It's going to use that to basically learn from all of this data and make actionable insights that will inject into all stages of the software development lifecycle, accelerating all those stages. And I'd like, again, to make that a little more concrete by mentioning specific tasks in the software development lifecycle that will be accelerated using AI. So anything green, all the green dots on this slide are basically tasks that are already being worked on by Tabnine or others. And I think we'll reach relatively high maturity in the next 12 months. So in here, you can find code generation for developers, training on your private repos and getting code that is specific to your patterns and your best practices, but also things like test generation, test prioritization and selection, picking which tests to run, automatic refactoring, and many, many others. I won't go over all of them. The purple ones are slightly further ahead, maybe not in the next 12 months, but we can already see them starting to materialize. So that things like dialogue-based diagnosis, being able to say, hey, I have a failure in production. Let me have a dialogue with the AI to try and understand, diagnose what's going on, maybe put the error message, then the AI asks some questions, and we're having a dialogue trying to diagnose what just happened in production. Similarly, automatic remediation of production faults, maybe some of the things that fail could be fixed by AI on the fly without getting you paged in the middle of the night, and all of those other tasks here that are going to mature over time.
Quick question on this,
so
Eran.
Yeah.
Sorry, just tying a couple things together. So I think would be interested, really interesting use cases. I know sometimes I've had the habit of perhaps thinking that the only gap between these use cases and a customer tends to be where the maturity of the, say, AI model is. Do you mind spending a little time, since for context for everyone, Tabnine has been at this for about 8 years now, 8 or 9 years. And was originally a company called Cadota, and we did it around Java completions before any of these large language models existed. I know one piece that maybe people should think about, we're seeing models that an API just being as an access to the model. What are the other important parts to making this real? UI, UX, maybe some other aspects that I think maybe are missed, because I do think like this is oversimplified a lot when we talk to people. And maybe if you would add a little context of your experience over the last 8 years of where models are important, UI, UX, like what are kind of the components that to make this something that people use?
Yeah, thanks for that question, Brendan. I think I'm going to dive into how this works and what are the kind of ingredients that make this work. But definitely UI, UX is one of them. The entire user experience for a lot of things, the human is actually the bottleneck and not the model. It is often you can think about accelerating a bicycle by strapping a rocket to the bicycle. That's not going to be a lot of fun for the human, right? So there are many better ways to accelerate things, and there are many opportunities for what we call misguided automation or misdirected automation. And I'll talk a little bit more about that, but definitely UI UX is an important part here. How do you get the model to work with the human or the AI to work with the human and not against them? I'll touch on that a little bit later, Brendan. Thank you for that question. Just as an example to make, again, things concrete in case you have not used Tabnine before, this is kind of the stuff that you can get with code generation with Tabnine and with other products as well. You can write it some specification as a simple comment, like create a student class with first name, last name, password, and quick password with SHA-256. And as you can see here, Tabnine generated this entire code here, and you can just accept it by tabbing through. So basically, software development becomes a two-player game. You give a hint of what is it that you want, and the machine generates the code for you. Then you can edit it, or you can ask some more questions or interact with the completions to kind of refine them to get really what is it that you want. As just, again, as another concrete example, you can now do test generation. You can look at a piece of code here. There's like a piece of code that finds the maximal element in an array, and you can ask Tabnine to generate tests for you. And you can see that it generates tests that actually with values to put in the array and finds the actual assertion to make sure that this procedure, the find max procedure, actually returns the maximal element in the array, and you get the diversity of test cases here, et cetera, et cetera. And there are many other use cases. I did not include the demos for all the features that I showed you, but I just wanted to show two concrete examples of what you can do with this technology. And there are many other tools and company, you probably heard about ChatGPT. There are things that are generating text. There are things that are generating images. There are things that are generating models that generate 3D models and many, many other things. And so really generative AI is everywhere, and it's going to change everything and all basically areas of our life. And generative AI is generally powered by large language models, or LLMs. For people not familiar, these are typically transformer-based models which reason about sequences. And transformer-based models have an attention mechanism that provides a general approach for learning relationship between entities in a sequence. So the model really doesn't care what is it in the sequence. The model operates over sequences of numbers, and the model captures or learns relationships between these sequences of numbers. So the same model, that's the beauty of transformer model, the same model works for natural language, or the same architecture, works for natural language, for programming languages, for music, for images, for videos. It just matters, like the only gap is how do you encode kind of the input, the image or the video for the programming language as a sequence of numbers that the model can reason about, right? And so LLMs are really transformer-based models that are becoming bigger and bigger all the time. And one of the interesting phenomena that people have observed is that these models present what is called emergent abilities as the models grow. So you train the model to perform a certain task over natural language, and suddenly the model becomes very good at answering things, at kind of solving tasks that it has not been trained on. And this is referred to as an emergent ability. And so you basically say, train the model to predict the next word in text. And when it becomes large enough, suddenly it learns how to answer questions, right? And this is like an emergent ability. This is a task that the model has not been directly trained on. But because it captures the relationship in the training data, because it captures relationship in the sequences, it is suddenly able to do these more, say, advanced things. And it's important to say that these emergent abilities are not present in smaller models, but become possible when the model size increases, right? So, Brendan, I'll pause here if there are questions, because I think it's just going to get more technical from here.
No, I was waiting just for you to finish here, because the framing of what you just went through kind of lands into where Mohammed had a question, which was really about, his comment was, hey, about having good taste in what good practices in software development are. And he refers to it as opposed to, say, being being good at mimicking what's out there on GitHub repositories or even an internal code repository.
Mm-hmm.
So this is, I think, hits. So I wanted to get through this pieces, but he's trying to understand, I think, some of the trade-offs of taking maybe a large amount over at GitHub versus training on a local. How should we think about what the implications are of, I think, largely around the training data set? Feel free to expand on that, but that's kind of his general question.
Yeah, so I think generally speaking, for all these models, more data is better. So you want to train the models on as much data as you can get. Of course, you don't want to train them on complete garbage. You want to train them on something that is slightly filtered for obviously, say, broken code. But other than that, I think you want to train it on as much code as possible. And what happens when you train it on a lot of code, because these models are very good at capturing patterns, and because good code is not as diverse as bad code, right? There are only a few ways to do something correctly, and there are many, many more ways to do something incorrectly. And so what happens is that the signal from the correct ways is actually becoming stronger, and the diverse cases that are not as good are basically sinking statistically. So you can think of that as, I like to think of that as the Anna Karenina principle, like, all happy families are similar to one another, but all miserable families are each miserable in its own way. So every miserable piece of code is kind of miserable in its own way, but good code is similar to one another. And this is why statistically kind of good code floats to the top. Does that make sense? I hope that makes sense, right? So, and that is correct not only for code, it's correct for natural language, it's correct for any other signal in which, the structure present in the correct kind of examples or the good examples is more limited than the way to do things incorrectly.
And Eran, a compliment here. So I like to also jump in from compliment coming in from David. Big fan of Tabnine, particularly the context. He's looking forward to if anything you want to add color, but can't wait for the PRMR component. He's been playing with some other NLPs and they were a little off for him, I would say, is what I'm interpreting his comment on. Loves the elegance. So I think this, I'm going to, David, feel free to push. One, we thank you. Two, I think you're pushing on that point of really the aspect of the user and giving the user the right code at the right time in the right place is all non-trivial, as it turns out to do really well. So thank you for the compliment. We got plenty of work more to do. And yes, the PRMR is a place that this has been a place Eran has been hacking away himself personally for quite some time. Eran, feel free to add color, but I want to say thank you, David, and that's true.
Yeah, thanks for that, David. I think maybe a general comment about this space. It is very easy to get a demo working, and it is much harder to get a product that provides value to customers working. And the MR, PR is an example. Like, we've had the beta of that almost a year ago, and we use it internally, and it just did not provide enough value for us to give it to customers yet. So we'll improve it over time, and it will reach you when it matures, hopefully towards the end of the year. I'd like to dig a little deeper on emergent abilities. And again, guys, feel free to kind of stop with questions because this is getting more technical. So here are some charts that basically compare different model sizes for different tasks. And you don't have to understand all the details here. Maybe we should look at one of them. Maybe truthful QA is interesting just in terms of an example. And what we see here is a task. Truthful QA is the ability to generalize over incorrect answers found on the internet. All sorts of like prejudice and stuff like that. You want to generalize, you want the model to be able to generalize above the few examples that demonstrate prejudice. And the x-axis here is the size of the model. The y-axis is accuracy. And as you can see, like while the model is small, you really don't improve. And suddenly when you hit a certain size, you get this radical improvement in the accuracy of the model. And if you look at all the graphs here, they all demonstrate a similar pattern, like precision remains very low for a while, but when you hit a certain model size, suddenly you get this emergent ability. Suddenly the model becomes much better. And the same thing happens for code. You train it on enough data, you train a large enough model, you start to get these emergent abilities, models that are able to say interesting things or to complete code in interesting ways, just by the sheer size of the model plus the training data. Maybe not obvious, larger model means that you need more data to train it. So when I say bigger model here, it entails that we're also using bigger data. And you're probably asking yourself, Eran, what are these large models, large language models? How big are they? And it's good that you asked, because that's what my next slide. And this is a slide that shows the size of modern large language models, again, LLMs. And this is just until December. I haven't been tracking, how the size increased over the last 3 months. You can see that there are models already out there that are basically around 500 billion parameters. This is Palm from Google. There are others like MTNLG, Bloom, that is open source. Many models here. GPT-4 is not here. It was not there in December, right? But GPT-3 is, with 175 billion parameters. So you can see these models are getting quite big, right? So I'd like to talk a little bit about like different avenues of research, or going deeper into LLMs. And basically there are 3 kind of general lines of research in LLM these days. One is scalable training of LLMs and scalable inference. Again, all images are generated, in this case, by DALL-E. This is why they look a little funky. I did not have the prompt here, but this says something like training a language model as a horse jumping through a hoop of fire or something like that. I don't remember. This is why it looks that way. So one line of work is scalable training of LLMs and scalable inference. This is, I will not talk much about it in this talk. I'll explain why in a second. Second is using LLMs, which I think is what's going to be interesting for a lot of you guys. And the last one is understanding LLMs, which I'll touch on. All right, so
a little bit.
Talk about this.
Yeah, I think Tomer had a question, and Tomer, you can validate if I'm off, so ping me. But if we go back 1 slide, sorry, I missed this, Tomer, I was typing away. His comment was, why do models have a point at which they become more accurate? Like, I think he's observing there's a little bit of a tipping point. What's the characteristic there that makes them all of a sudden, the jump up here?
Yeah.
All right, yeah.
So the short answer is nobody knows. And
thanks, Eran. Come on.
Yeah.
You're the Oracle of all things. And the answer is we don't have an idea. That's cool.
It's a research question. I can put some papers later in the chat that say we don't know in more words, but the bottom line, is that nobody knows, and I'll touch on that maybe when we talk about understanding language models towards the end, because I think it's interesting. But it's an excellent question. It's an excellent research question. Nobody knows. Maybe a little more refinement of that is, we know that something deeper is going on, but we don't know how to distill it. And so until we know how to distill it, we basically brute force the future by using bigger models. Once we understand kind of the underlying principle and what is going on here mathematically, or in a kind of a principled manner, I think models will start shrinking back to something manageable. Right now, because we don't know, we just throw more parameters and more data at the problem. All right, so I want to talk a little bit about using LLMs, but before I do that, I just want to maybe mention why I will not be talking about training LLMs. So without explaining exactly what is like petaflops and like compute cost and stuff like that, what this graph is showing us is just basically the compute required to train modern models and how it changed in the past 2 years, or maybe a little bit more than 2 years. If you look at like GPT-1, the amount of computation you need to train it was whatever, let's say around 50K petaflops, which is quite a lot. But now we're over like trillions of petaflops around here for the modern models. And I don't want to get like too technical on what it means in terms of compute, so let me simplify it for you. This is like millions of dollars. And so if you want to do kind of research in this area, if you want to explore training new models, you better come up equipped with a few millions of dollars to train these things. And so in the rest of this kind of webinar, I'm going to talk about using LLMs as a black box mostly. And as I said initially, you can think about it as a model that takes an input sequence. And again, the sequence can be coming from code, it can be coming from natural language, can be coming from video, from images, or from whatever. And at the end, the output is a predicted output sequence. So that's the game. But of course, in reality, and Brendan alluded to that a little earlier, models are never used this way. What actually happens is that you have a bunch of pre-processing stuff that is being done to the sequence before it goes into the model, and have a bunch of post-processing stuff that is done when the sequence or sequence sets go out of the model. And in particular, you can do all sorts of prompt engineering, which I will show you examples of, hinting, helping the model by giving it hints, context awareness, kind of trying to push more context into the model so it makes more accurate or more context-sensitive predictions. And in the post-processing, you have things like trying to score the suggestions. Is this suggestion good or bad? Let me try. Is the output sequence good or bad? Let me try to put a score on it. I can maybe try to filter it if it doesn't match certain semantic conditions, or I can try to use other models to filter it. So actually, I should be clear that both in the pre and the post, you can have other LLMs participating. So it's very typical actually to have models both in the pre-processing, in the post-processing that are kind of helping the LLM in the middle. All right, so typically like a system that is using an LLM is not just the model being driven by sequences. There's a lot of stuff going on to make sure that what you get from the system, even before you get, Brendan, to UX and UI, just purely the backend, let's call it, it already has a lot of complexity around the main model, maybe with other kind of secondary models, both in the pre-processing and in the post-processing. And it can be more than one inference request. So there can be some loops here and other things. So, building an ML-based system is not just taking a model and deploying it. So let me show you a few examples here. I think that would be useful. And I'll actually like to start with an example of natural language. So if you give the model the sequence, the fastest mammal is, the model can typically predict something like the cheetah, which can run speeds of up to 75 miles per hour, right? So that's kind of easy. And in this webinar, I will use text with green background to denote predictions from the model. So you will see that repeating in kind of the next slide. All right, so I can do the fastest mammal is the cheetah. All right, we already saw that. But now I can ask it, a brown horse is likely to run faster than, and the model predicts a white horse. Brown horses typically have higher levels of muscle mass and energy capacity, which means they can reach higher speeds than white horses. And so I have no idea if that's correct.
Is this true? This is not true? This is new facts. My daughter who loves horses, it's important to know. I guess we should check Kentucky Derby. Is the Kentucky Derby only does have darker horses? Could be true. We're going to have to double check this. Eran, I'm double checking you on this right now.
I think so one of the interesting things about these models is that they give answers or predictions that may seem completely plausible. And in this case, maybe, I don't know, it's pretty hard for me to actually say. And you can take it to like factual questions like the Prime Minister of Bulgaria is, and it gives you something. That I know is incorrect, actually. So it's just based on because the training data doesn't reach recent history, et cetera, et cetera. So I'm going to skip like the favorite food and all sorts of other questions, right? So But let's go to more mathematical questions, which are interesting. Okay, so let me pose this question to the audience. Maybe they can write in the chat what they think the answer is. So we have basically a high school math problem here, which is a line parallel to y equals 4x plus 6, passes through the point 510. What is the y coordinate of the point where this line crosses the y-axis? So I'll give you like 30 seconds.
Good. I'm going to start. If I had Jeopardy, if I'd known this ahead of time, I had the Jeopardy music, so we could go with the Jeopardy music. And I'm waiting. So first one in.
Yeah.
No pressure,
First one
y'all.
in. Yeah.
Pull out your graph line paper. Feel free if you need a ruler. Both of these go back to.
Yeah, I think they should. I think they can just put in 5 and 10 into x and y, and find out what's the
Y equals
slope.
10, x equals 1 is the answer from Amirsky.
Amirsky is doing math. All right, Amirsky, let's see if you got it right. So the model says the y coordinate of the point where this line crosses the y-axis is 0. This is incorrect.
Well, Amirsky, you fail. I'm sorry, I'm just kidding. That's terrible. I'm a terrible host. I'm now a jerk. I'm both a bad host and a jerk at the same time. I'm going to lose my job. Keep going.
So this is not right, and the model made a mistake. And now, one way that we can help the model, or a general principle for helping these models, is called few-shot prompting. And the idea is that what we just showed the model previously was too hard for the model. So let's help LLMs solve challenging problems by showing the model a few examples that will help the model reason about it. Examples are provided as part of the prompt, so you don't need to train anything. You just use the model in a different way. Rather than giving it just a sequence of the question that you want, which I refer to as a prompt, you also give it some examples of what is it that you want the model to solve. So no update of model weights takes place at all. And this has been done very successfully on a wide range of domains. So common sense reasoning, mathematical reasoning, symbolic reasoning, all sorts of other things. And the idea is the following. Again, let's look at mathematical reasoning. And what we just had is mathematical reasoning, right? We had this line parallel to blah, blah. So we need the model to do some mathematical reasoning. So rather than giving it just this question, what we're going to do, we're going to give it a lot of examples. So we're going to give it like a sequence of problem, solution, problem, solution, problem, solution. And you see that the problem is like find the domain of the expression, blah, blah. And if you've ever written text in LaTeX, scientific papers, you will identify the syntax. So this is a particular syntax that actually kind of separates the mathematical part with these dollar signs very explicitly, right? And you can see that we give the model examples of problem and then the answer. And I'll just give you a hint to what is going on to happen. At the end of every answer here in the examples, we have the sentence, I hope this is correct. I hope this is correct. So we're actually teaching the model to be polite as well, right? So we're giving the models as part of the prompt, as part of the input, we're giving the model a few examples of problems and solutions. And after we give it all these things, right? So at the end, some other solutions for the first problem, we also feed it the problem that we originally had in mind, which is this line parallel to y4x plus 6. And now what the model produces is this solution. And you can see that the model now, rather than just saying the coordinate is 0 incorrectly, it now follows the examples that we gave it. And it gives us a very elaborate explanation. It says, since the line is parallel to this, the equation is this. And since the line passes through 510, we substitute the values, blah, blah, blah. And the final answer is minus 10. And as you can see, this is correct, actually. And as you can see, it also tells us, I hope this is correct, because this was the structure of all the examples that we gave it. They all ended with, I hope it is correct. So it learned to kind of say, I hope it is correct at the end, but it also learned that it needs to go through reasoning steps before jumping to the conclusion. And by forcing it, or by kind of demonstrating to it that we want it to go through reasoning steps, it became better, because it kind of, we forced the model I'm hand waving here, but we force the model to verbalize its thinking rather than just jumping to the final answer. And because
You
the
forced
model
it
has
to
been
be,
trained.
can I use this with my kids so I can force my kids through this process to be both polite and to show all their work? Because like that's
Yeah.
nice. I'm not sure that I can learn how to do that as a parent, but you can do it to a
Yeah.
model.
So yeah, absolutely. You can do it to the model. And this is from a paper on mathematical reasoning using models, which was mentioned, I think it's this one. I'm pretty sure. So, it's pretty simple. We did not train the model again. We did not change anything. We just interacted with the model in a different way to get the model to do what we want in a more reliable way. And so you ask yourself, okay, so once I've done this, am I done? Like, can I do this for everything? And let's do some math word problems. So here's like an example. We'll try it the same way. So we'll try to give an example to the model and then ask the question that we actually want to answer. So the cafeteria had 23 apples. If they used 20 to make lunch and bought 6 more, how many apples do they have? Answer 29. Interesting. That's obviously incorrect. So the model failed. And we're going to apply kind of the same idea. And this idea is called chain of thought. We're going to show the model examples that break the reasoning into steps. So instead of showing the model just the example, wait, hang on. Instead of just showing the example where Roger has 5 tennis balls, et cetera, and the answer is 11, we're going to show the model an example that, again, forces the model to show its work, as Brandon called it, right? So we have this question, and now we force the model, or we show the model an example that it has to show its work, and now it says, okay, 2 cans of 3 tennis balls, each is 6, so actually, the math exercise that I have to solve is 5 plus 6, and the answer is 11. And sorry, I did not separate this correctly. And now we'll have the same question. And now the model will again show its work. It will use chain of thought. It will verbalize the reasoning in the answer. And it will say the cafeteria started with 23 apples, 20 were used. So the math exercise to be solved is this one. And the answer is 9. All right. So again, we kind of did this chain of thought thingy, and the model got the correct answer. So I'm going to skip a little bit because I see that
some good context here, Eran. A good question that I think. So I'm going to kind of 2 pieces, and Bjorn, I'll get to yours because you have this size, but I think it sort of fits in the end. Frank was kind of asking the question: is there any way you can know whether if it's the model or the lack of data that is the problem? And is there any easy way to spot that, or how do you know which is your limiting, I think, factor in getting a good answer?
Yeah, I'm afraid I don't have a good answer for that. There are definitely things that are out of domain. I think if you are the person training the model, then you are familiar with the training data that you fed in. And when you get an incorrect answer, you can maybe diagnose that you have a certain gap in the training data. But other than obvious gaps in the training data, it's very hard to diagnose whether this is like a gap in the model or a gap in the way that you are asking the question. So I'm afraid I don't have a good answer for that. Yeah.
So that is a little bit, there's a data. Yeah, so there's a data question. There's a little bit of prompt question on how you answer question, which you kind of hit before, that oftentimes has in terms of what a model gives back. I'm actually bring in actually Bjorn's question a little bit here, which is you spoke earlier about size of model, size of data. Maybe help understand, like, does it matter just no matter what, a bigger model is amazing, or the data matters a little bit of what those trade-offs are in when you're building and when someone's running and using a model? And I think I will speak for Bjorn, which is a bad idea, but I'm going to speak for him anyway, and you can tell me, Bjorn, I was wrong. I think oftentimes what we hear, or I hear all the time talking to customers, others, is, oh, the bigger model is always better. And so I think there's that notion in the data. So how do those kind of interplay as we move through this space kind of going forward?
Yeah, so bigger is not always better, especially not if you're doing a particular task. If you're trying to build a generic model that can handle all tasks in the world, like multi-purpose, general purpose model, say GPT-4 style, then definitely bigger is better because you're trying to kind of get it to solve everything in one model. And I think that's generally very hard, right? So, but for particular tasks, say code completion, test generation, these kind of like more narrow, let's call them tasks, bigger is definitely not always better. A lot of the barriers come from what we call scaling laws. So when you go to a bigger model, you need much more data to drive that model to be accurate enough. Otherwise, it remains undertrained. And so a bigger model entails more data. More data entails maybe including lower quality data. And so there's not bigger is always better there, right? So it's more nuanced than that.
There's one other hit, depending on who's doing it. We hide this. The bigger the model, the more expensive it is to both train and run. So there's a lot of implications on this. As my previous answer before, this is very much like Formula One. It's a good place to waste a large amount of money if you don't know what you're doing. So
yeah, absolutely.
Yeah. Yep.
Absolutely. I wanted to kind of show a more complicated example when chain of thought is not enough and kind of get to the idea, which I think very compelling here. So let me just go to the next one. Here's another math word example, which is more complicated because now we have bakers in Beverly Hills Bakery, which start with 200 loaves of bread, sell 93 in the morning, 39 in the afternoon, but also return 6 unsold loaves. And so, you need to do some complicated math here. And actually, the model gets it incorrectly because this 6 should be subtracted and not added. And the question is, how do we solve that? And so chain of thought was not expressive enough to capture structure of the desired computation. I think here is a pretty powerful idea coming from my former student, Uri, who is now a postdoc at CMU. And the idea is to show the model examples that generate a program that solves the problem and not examples that solve the problem. So basically what this does conceptually is offload the problem solving to a separate solver, in this case, the Python interpreter. So before, when we did chain of thought, we kind of showed the model an example that required the model to show its work, right? How did you reach the conclusion that the answer is 11? What we're going to do now instead is basically give it a prompt that demonstrates the creation of a program from a question. So if you take the question that we just had with the bakers, what we're trying to do, rather than generate the answer, we are generating a program that when you run the program, it will get the answer, right? So we translate the word problem into a Python program. So in this case, you take this word problem that talks about the number of loaves of bread, and you basically generate a program that has loaves baked, ones sold in the morning, sold in the afternoon, the ones that are returned, and you get this kind of math equation here that computes the right number of loaves at the end, and then you return it. And so basically the idea is to have program-aided language models. So the language model does not compute the answer. The language model computes a program that, if you run it, will return the answer, which I think is extremely elegant and beautiful in general. And since then, there has been some other papers around this. One of them is called Toolformer from Meta. And what this does, it teaches the model how to use external tools. So the model generates not the answer, it generates calls to other things that can produce the answer. For example, in this case, if you ask it the New England Journal of Medicine is registered trademark of, then the model will generate the query to a Q&A engine that is able to answer this question. If you ask it out of 1,400, 400 participants, then it will call a calculator to compute the result. And the idea is that, again, the general idea is that the LLM does not need to learn things you already know how to do, right? A calculator is pretty good at solving addition or division problems. You don't need to teach an LLM how to do division. If you want to teach it how to do general division, you will spend a lot of parameters, waste a lot of parameters on things that you know how to do symbolically, right? Because you're teaching it to solve these problems the wrong way. And so currently the trend right now is really to make models smaller, but have the model kind of generate queries or generate programs or generate problems that can be offloaded to special solvers in a particular domain, right? So it's the same idea like generating a program, but now instead of generating a program, we're generating an API call to something else that can maybe answer the question. A calculator would have helped us also in the baker's problem that we had earlier.
That's awesome. Interesting. So, Eran, I'm throwing you a curveball here. So, Ronan's going to give me one that I am not sure, but it's a test. Hey, as a professor, no challenge here, but he says, does the alpaca demo from Stanford relate to the answer about the size and the data? I am not familiar with the alpaca demo, and I'm guessing since you are in the academic realm, it's a chance you might. I also asked him to add a link, so maybe a link, but if you know, this might be fascinating.
I'm familiar. It's somewhat related, but alpaca is really just fine tuning, and so it's a separate discussion. You start with a very large model, and then you can fine tune it to a particular task and make it even better. So there's definitely a lot of merit to that, but again, I think it's just not in the scope of what we can cover in the time that we have left. But by the way, in terms of time management, I have no idea. I can talk forever, so you guys will have to stop me.
I think we're getting a little bit towards the end, but I think we've covered a lot of it.
So I just maybe
I'll get your question, but you're good. Eran, you go ahead.
Yeah,
finish up.
Maybe a couple more minutes. Maybe a couple more minutes just to wrap this up. So using LLMs as black box is quite brittle at the end. What I showed you is both examples where natural language is kind of hallucinating and making these, I don't know, statements about black or brown and white horses, whatever that was. But it is very effective for many tasks. Sometimes the model gets things wrong and we have no idea when. So the model doesn't say, here's my prediction, but I'm not sure. The model is not modest, right? The model is like, here's my prediction, good luck, right? And so it's hard to say when the things are wrong. Also, it's worse. Results may vary drastically due to minor changes in the input sequence. So you can get the same white brown horse example and maybe change where the comma is in the input and get a completely different answer. And in terms of research, many fundamental questions are open, like how many transformer layers are required to solve a particular task? Is there some lower bound? Can you tell me, hey, you cannot teach transformers to do division unless you use 7 transformer layers or something like that? So there are many kind of interesting questions, and also questions of, can we provide some computational model for transformers? Can we explain mathematically how these things work and what exactly is it that they learn in terms of accomplishing a task? And maybe this will be again the topic of our next webinar, I guess, because I can keep talking, but maybe we should stop the question at this point. I'll just say that in terms of understanding LLMs, magic is just science that we don't understand yet, and we're definitely in that stage. So what these models do look like magic, but we really don't understand how they operate in a fundamental way. Yeah. So go ahead.
I think we got the one question. We'll sort of finish up. If anyone has one last one, ping me real quick so I catch it. But I think I'll answer a little bit on this one because actually I looked it up. So hey, I get to answer a question. I have to add some value. So Bjorn was interesting, sort of like size of GPT-4. I believe, I'm not sure it's fully released, but I think this is in the 100 trillion parameter size, if I'm not mistaken. Some fun facts around that. So no?
I don't think it's
Nice.
100 trillion, but I don't
Nice. I was
remember.
wrong. So I even come and I look it up and I'm still wrong. So Eran, sorry to
I
correct.
think there's a lot of misinformation out there
Okay.
on the size of models, but yeah.
Yes, they will take. It does appear that this is taking a small supercomputer funded by Microsoft to build, run, and train it. So it's a lot of fun, but this is HPC style fun on these really, really big models. So we're going to see. It's going to be interesting. To be clear, just so everyone's sort of on this space, because Tabnine focuses a whole lot on like a smaller subset, although very large in code. Clearly, we do not need to use a GPT-4 model. As much fun as it does cool things, it is not the code we use and the specialization and all that is what we focus on in helping our customers get the most out of it. So just for context, it's a pretty, even this space is relatively wide, and areas we focus is relatively speaking pretty narrow. So Eran, anything you want to add on that? Any context as people are thinking? We're happy to jump in with anyone. Send us emails. We'd love to jump on it. We will, I think, sure, Sharon, I believe we're going to be posting this. So for those of you that came a little late and asked the question, we'll have it available for you all. Eran, I think that's it. Anything else you want to add right at the end?
No, I think we can stop here and continue in the next webinar. I can talk much more about understanding LLMs and like the details of that. I think it will have to remain for the next time.
Wonderful. Well, you all, we so appreciate you spending some time, whether it's earlier morning stateside, later evening, if you're over here in Israel or in EMEA. And we look forward, we will keep trying to send some fun stuff your all's direction. If you have any fun ideas or anything, also send them to us. As you've noted, we have Professor Eran on, and this is kind of his thing. So Eran, thanks for spending the time with us. And for all of you, we will talk to you soon. Let us know any way that we can help you, your companies, and what you guys are up to. We'd love to be a partner to you. Take care all.